my name is Jacob Post. My project for the RIPP program was the role of turbulence pressure on the acceleration of solar wind. And my two mentors were Dr. Laxman Adhikari and Dr. Bingbing Wang in conjunction with each other. So let's begin. So just to start, I'm going to begin with a brief overview of solar wind. So in a general sense, solar wind is essentially a plasma that forms along the surface of the sun and at some point expands outward into the heliosphere. And so the journey that it goes through will eventually lead to an encounter with Earth. And this encounter leads to phenomena occurring such as the northern lights, which are very cool. Solar wind is influenced by a variety of different factors, including density and pressure. For the sake of my research, the main factor that I was focusing on is turbulence. And so that kind of leads me into research paper. So the purpose of my research paper is to see how turbulence pressure affects I guess, capability or ability of the solar wind to accelerate to any given level. And so on this slide, I have included two different figures. One of them showcases temperature versus the height in solar atmosphere. And so you can see that at the surface of the sun near the corona is where temperature is hottest. And so what this essentially reveals is that at this point, pressure will also be very high, which will lead to some form of acceleration experienced by solar wind. And so that kind of leads into the other figure, which talks about the solar speed versus the heliocentric distance that the solar wind has traveled. And so you can see that initially it is a sudden increase of solar wind speed, and then over time it tapers off as it travels further away from the sun. And so before I go into the actual process of doing my research, I need to introduce some fundamental variables that will be important to understanding the equations that will be found in this presentation. So as you can see, there is quite a variety of them, about based off of my estimate, like 25 different variables, and each of them will play a factor in their own specific way in the fundamental equations that I am about to introduce. And so these fundamental equations will be the cornerstone in which I am able to answer the question of how turbulence pressure affects the acceleration of solar wind. And so this will be the moment where I basically talk about my general strategy for going about my research. So in order to see how turbulence affects solar wind, I split my research into two different scenarios. One scenario will cover a instance in which there is no turbulence pressure applied to the solar wind. So that will act as like a baseline for the research. And then I will have another scenario where turbulence pressure is included in the scenario. And so at the end of my research, I'll compare and contrast the resulting graphs that I'm able to obtain from working through these two different scenarios. And so for my first scenario, the main three equations that I'll be working with are the top three, which are the continuity equation, the pressure equation, and the momentum equation. For the case in which I will be including turbulent pressure, all six equations found on the screen will be utilized. And before I move on, I need to make one clarification. For the correlation length, I made the simplifying assumption that lambda d is equal to 2 lambda plus or minus. This essentially simplifies the equation to a point where it's easier to work with. And so the first step when working with these equations is to simplify them, because in their current form, they are unsimplified. So simplifying them essentially allows for them to be easier to use, and that makes the entire research process a little more streamlined. And so from top to bottom, we can see some slight variations in the equations as compared to what they were before. We can see that the continuity equation will be primarily responsible for the change in density in comparison to the change in heliocentric distance. The pressure equation will be in relation to change in pressure, and the momentum equation will be in relation to change in solar speed. And so another clarification I'd like to make real quick is that present in some of these terms will be or would have been a gamma variable. And this gamma variable, depending on its value, determines if there will be a turbulent heating term included or not included. So the gamma term essentially determines if it's a simplified scenario or unsimplified scenario. And so for the simplified scenario, gamma will be equivalent to 1, or in other words, it will be an isothermal case. And then in the turbulent pressure scenario, it will be equivalent to 5/3. All right, now that we have our simplified equations, our next step is to normalize them. And so what normalization is that it is a mathematical process that works by relating a standard variable to a constant and normalized version of itself. What this basically allows for is basically like a check for the equations that I have listed out in the previous slide. When normalizing an equation, you are able to determine if your equation is right or wrong, depending on if the units that are present in the equation are able to cancel out from each other. So through normalization, you are essentially able to ensure that the equations that you are using are correct. Another benefit of normalization is that it allows for some simplification of the equations used. It allows for a more streamlined method of thinking and in the future programming. So using these normalized equations, I will be constructing the graphs needed to showcase both scenarios that I have mentioned earlier. So to begin, I will showcase the normalized fundamental equations for the first 3 equations. The reason I did this is because these 3 equations will have 2 different forms in themselves. Obviously, one where it's an isothermal simplified gamma equals 1 case, and another where it's a turbulent pressure case. And so on the left side, we can see the gamma equals 1 simplified case. These equations are slightly more simplified in comparison to their counterparts on the right side. And so from this, we can already tell that obviously turbulent heating has a lot of impact on how the density, pressure, and solar wind speed basically change over time. And so this next part, I essentially is just introducing the 3 normalized equations for the equations that will be used in our more complex scenario or turbulent heating or turbulent pressure scenario. And it may look like a lot right now, but trust me, it is slightly easier to work with these equations and create a program that is able to accurately create the graphs that we are looking for. And so before I continue on to the code that I wrote for both scenarios, I need to talk about the sonic point. And so the sonic point is essentially the point where the sound speed and the solar wind speed are the same. Finding this sonic point is important because passing through it allows for our curves that are created with our programs to converge. In cases where the sonic point is not met and passed through, our curves tend to diverge, leading to data that we can't really use to come to any foregone conclusions. So included here at the bottom, I added my process for finding the sonic point equation. What it essentially entails is taking the momentum equation that is normalized from before and performing a L'Hopital's operation on it, which is essentially taking the derivative of both the numerator and denominator of an equation. And so what we'll find is that at the end, we are able to create a quadratic equation. So plugging our values into a quadratic formula, we are able to create a sonic point equation that can be seen at the bottom right of the third picture I've included. So using this sonic point equation and the previous three simplified equations mentioned, I am able to write a code that creates graphs for solar wind speed, density, and pressure. And so here, I'll explain my code. So what I've done, I've essentially created two different functions, each with their own set of initial conditions. And within these functions, I've included the fundamental equations, the momentum continuity and pressure equations as a system of ODEs. That is for the top function. And then for the bottom function, what I've done is essentially replaced the momentum equation with the sonic point equation that was found before. Since the sonic point equation is essentially just a concentrated version of the momentum equation. And so using these two functions, I am able to essentially write a code that creates two different boundaries from a certain heliocentric distance to another, and run a while loop that creates intervals in which either the top function is used or the bottom function is used. And so the results of this program, unfortunately, were lost in translation. Something went wrong with the graph towards the end of the internship, so I'm unable to show it to you now. So instead, I have found a graph that is similar to what mine would have looked like. And so from this, we can see, similar to the figure that I showed at the beginning of the presentation, the solar wind speed tends to increase suddenly, which makes sense. When you think about it, solar wind tends to move away very quickly initially, and then as it gets further out from the sun, it tends to still increase, but just not as quickly as before, which is seen in this graph as well. As you can see, it increases suddenly and then still increases, but just gradually. Towards the end of the graph, at around 100 solar radii, we can see that the solar wind speed ends at a value at approximately 400 kilometers per second. And we're going to keep that value in mind moving forward. And so moving on to our more complex scenario, I have to introduce a few more equations that will be required to find the most accurate answer to the turbulent pressure scenario. And so while they weren't included in the fundamental equations list, they are still pivotal towards finding the answer. So these equations are the Alfvén velocity equation, the normalized Alfvén velocity equation, the normalized magnetic field equations, and the normalized turbulent heating term equations. I would just like to add that these equations were actually utilized in previous slides. It is just in this slide is where they have been formally introduced. So using these equations, I was able to write a new code. And what this new code did was similar to the last one. It essentially took two boundary conditions for the heliocentric distance, and it took a function that I've written, which is here, and it treated all the equations mentioned before, both the fundamental equations and the important equations mentioned before, and it treats them as a system of ordinary differential equations. This function will solve those systems of equations, and it will create graphs that show how different values change in relation to the heliocentric distance that is covered. And so here are the results of that program. So I would like to clarify that due to a time constraint, I was unable to find the sonic point for both scenarios. I was able to find the sonic point for the simplified case. Normally, there would also be a sonic point for the turbulent pressure case, but for the sake of time, I was unable to calculate that. If I had more time, obviously I would have gone back and found that. And so on the left, we can see that similar to the simplified equation, the solar wind speed gradually increases with a little bit of inconsistencies towards the second half of the graph. I believe that maybe because of just some simplifying assumptions that were made earlier on in the research project, but I digress. And so towards the end of the heliocentric distance interval, it only goes up to 13.3 in comparison to the 100 solar radii that the simplified case went to. But we can already tell that it is reaching a similar speed in less amount of time. Moving on to the center graph, we have a density versus heliocentric distance graph. What this essentially shows is that the density starts at a high point, but then gradually parabolically decreases without any signs of inconsistencies or discontinuities. Similar to that, but working inversely, the energy density moves upward without any type of visible discontinuity or inconsistency. So now that we've seen the results of both scenarios, what conclusions can we make? In simplified terms, we can conclude that turbulence increases the acceleration of the solar wind as it travels outward into the heliosphere. And due to it increasing the acceleration, it also increases the solar wind speed that is achieved by the by the solar wind. And so with that, I'll move on to some final remarks. Overall, this was a great opportunity. I had a lot of fun and I learned quite a lot about plasma and just the research process in general. And while I may not continue plasma research in the future, I do intend to apply what I have learned here to my career as an aerospace engineer, because part of what I believe is that plasma and plasma technology is the way of the future, and that utilizing it in the aerospace engineering industry will be pivotal to making significant progress towards our goals. And so that ties into my last bullet point there. I'm eager to see how plasma technologies affect the aerospace engineering industry and other industries that are interested in that technology in the future. And so before I end, I would like to acknowledge the people that allowed this research opportunity to occur. I would like to thank FTPP and NSF for funding the program in the first place. And I would also like to thank RIPP for being the ones to orchestrate and organize the research done here. Moving on, I would like to extend a huge thanks to my mentors, Dr. Adhikari and Dr. Wong. Without them, I would not be nearly as informed about plasma science, specifically in my field of research, as I am now. So I would like to thank them for being patient with me and for fostering my growth and understanding. And finally, I would like to thank my coworkers, Lucien Treville and Jason Jenkins, for creating a relaxed work environment that still allowed me to get my work done in a timely manner, but at the same time, making my internship experience all the more enjoyable. And so this last slide is just a works cited slide. And with that, that is the end of my presentation. I'd like to thank you all for listening to me ramble on about my project. And if you have any questions, let me know.
So my name is Lucian, and this summer I worked under the advisory of Dr. Laxman Adhikari. My project was examining the turbulent nature of the solar atmosphere and solar wind. So today what I want to talk about is a brief context on what it sort of means to study the solar wind, and then sort of the process that we took for me to clean the data, calculate these special variables, and then do some analysis on them, and then just the outcomes of this. So first things first, we have our lovely sun. Now, the sun is made up of several distinct regions, but for this summer, I was only concerned with the corona being the outermost part of its atmosphere. And so something that's kind of odd about the corona is that you expect the temperature to go down as you get further from the sun. Is that, as you can see on this graph on the bottom left, we actually see a massive spike in temperature right towards the corona, and this is still an ongoing area of research. So this is what I was trying to work on this summer. So the solar wind is a constant stream of, say, energetic particles, primarily protons and electrons, but it is made up of a lot of trace other ions. But so it's being ejected out of the sun's atmosphere. And we believe that studying properties of the solar wind, especially its turbulence, very well may reveal crucial insights to why the solar corona heats so far out of the sun. Um, I need to touch on something called alpha waves, because my entire project is based off sub-alpha intervals. So alpha waves are a type of plasma wave where the ions oscillate due to a restoring force from the magnetic field's tension. They were discovered by Hans Alfvén, who kind of kickstarted the entire field of magnetohydrodynamics, which is crucial for plasma physics. Um, Most interesting things about these waves is they propagate right along the magnetic field lines. And so the equation to obtain the alpha velocity is shown here, where we take the magnitude of the magnetic field divided by the square root of the magnetic permeability of free space and the plasma mass density. Okay, so how did we get our data for this project? Well, so I used data from the Parker Solar Probe. And so the Parker Solar Probe is a NASA mission, as they put it, to touch the sun. So they want to get as close as we have ever been to the sun and bring back as many recordings from the sun. This is extremely cool and brand new for humanity. So yeah, I got to work with data from the sun, and that was very neat to do. The PSP has data ranging from, I think, 2018 all the way to 2024. I specifically used data between April 2021 to October 2023, as you can see with the pink bars on the bottom of that graph. So I have data for about 10 encounters with the sun. Okay, so now the data cleaning. You can get all of this data. It's publicly accessible, but it will come in these files called CDF files that are massive. And so the first thing I needed to do was kind of clean up all the unnecessary data and move them to CSV files only containing what I actually need to work with. Another thing too is this data comes in several different time resolutions. So say electron density might be recorded every half second, whereas the magnetic field might be recorded every 3 seconds, and there's a lot of odd measurements. So I reduced them all down to a 1 minute resolution. So for every 1 minute, I just average it down to one value. So now all of my values are 1 minute apart. Another weird thing is there's a lot of missing data from the Parker Solar Probe. And so if the holes in my data were 10 minutes or less in length, then I interpolated them. Otherwise, we let them be because we didn't want to compromise on the accuracy of our data. Um, Calculated the magnitude of the magnetic field. Something I want to touch on is until this summer, I did not know about the RTN coordinates. For computer science major, I don't really do astrophysics. So the way I explain it to my family is it's just our regular 3D XYZ coordinate, but for space. So we have RTN. Um, but yeah, so using the alpha velocity equation on the last slide, I calculate that, and then I find the ratio between the radial component of the velocity and the alpha velocity, and we call that the alpha Mach number. And so if that number is less than 1, then that tells us we're moving slower than the alpha speed, and we are thus in a sub-alpha interval. The next step of the project was to calculate these variables called the Sasser variables. Plasma physicists love these. We wanted to see also the difference between the parallel and perpendicular components of all of our variables. And so using these equations from a paper from Adhikari, I split the magnetic field and velocity fields into parallel and perpendicular components relative to the mean magnetic field for a specific interval. Um, If there's any questions, I can elaborate more on these equations, but they're just a lot. Next, now that we've split all of our variables into perpendicular and parallel components, I want to see what the fluctuation is for each point in time. And so we denote this by lowercase b for the magnetic fluctuation and lowercase v for the velocity fluctuation. And so that's just the value at that point minus the average value for that interval. And now that we have all of those, we can calculate the Alsacer variables using that nifty equation at the bottom where we have velocity fluctuation plus or minus the magnetic fluctuation over the square root of the magnetic permeability and the average plasma mass density for that interval. Doing this calculation, we now have 6 L-Sasser variables. So 3 for the RTN components and then 3 again for the perpendicular and parallel components. Something to note is we can have the Z plus or the Z minus. Now, if the radial component of the mean magnetic field is greater than 0, we associate Z minus as being directed outwards from the sun and Z plus as being directed inwards towards the sun. Otherwise, the directions are vice versa. Okay, next. So the next stage of this project was to calculate the power spectral densities and the spectral indices. So power spectral density is a method of demonstrating the power content against the frequency of something. Um, so I took all of my data that was in the time domain, being read every 1 minute, and I brought it to the frequency domain using a Fourier transform. Um, and then I did some more math to make it PSD. But so we smooth these values down to make the calculations and visualizations more agreeable. As you can see on this plot, the blue is the original calculated values. Um, and while that's fine and dandy for this one graph, as we keep working with the PSD values and keep abstracting away, it tends to be helpful to smooth them down a little bit. And we also summed the RTN components to just be one value. Um, as you'll notice, this graph is in log scale. So when the RTN components are different by orders of magnitude, summing them together only shows a minor difference. And so here are the power spectral densities for the velocity fluctuations on the top left, magnetic fluctuations top right, the Alsacer plus variable, and Z minus on the bottom right. Now, throughout this presentation, the orange color should always be corresponding to the perpendicular component and the blue color to the parallel component. Something I want to highlight that is a bit odd. On the bottom right down here, we notice that the tail of the perpendicular component is less than the parallel component. And as you'll see through the rest of this presentation, this is pretty odd. We seem to expect the perpendicular component to always be greater, so we're not too sure about that. More on oddities. So plotting all of the PSD values for all of the sub-alpha intervals I obtained, we wanted to see how they would differ based off their distance from the sun at time of recording. So here we have these colored graphs. Yellow corresponds to further from the sun, dark blue closer to the sun. So you'll see generally the closer we are to the sun, the greater the PSD value. But we were expecting this to be much more clear and less messy as it is in these plots. And we also have the colored PSD plots for all the Alsacer variables. Another oddity, if you notice, there is a large spike towards the right-hand side of each graph. After some investigation, I'm still having a tough time declaring what that is. So future efforts on this project should be dedicated towards cleaning up these colored graphs and identifying why these spikes are here. Okay, bringing it back a little bit to just one interval. So on these graphs, you'll notice there's kind of a less jagged tail and then a much more jumpy region. So we call that jumpy region the inertial range, and we're mostly focused on that. So we can fit a power log regression onto the inertial range. And so you'll see here on the red fit, we get 197 times the frequency to a power of negative 1.18. That power is what we call the spectral index. So we were curious about, does the spectral index significantly differ with distance from the sun? And so here we're plotting the spectral indices for all of the PSD uh, intervals for the magnetic fluctuations, velocity fluctuations, and Alsacer variables. Now, the light blue in the background is the original values. You can see they're a bit scattered. And so the red error bars are the mean for bin size and then the standard deviation being the bars. Next, we also wondered, what if we just integrated underneath the PSD line? Um, are we going to see a trend in that? Surprisingly, to my surprise, yes. There's quite a clear trend. So when we integrate the PSD values, you'll see the orange corresponds to the perpendicular is much greater by like about an order of magnitude than the parallel components. Same thing here where the light colors in the background is the original data, and then the error bars are the binned data showing the mean and standard deviation for those intervals. We also have them. Oh, okay. Next, we wanted to know, looking at this data, it's clear that the perpendicular components tend to be greater. And so what if we took a ratio between the perpendicular area and the parallel area? So that's what these plots are showing. Yeah, same sort of thing where we have the light color in the background for the original data and the error bars for the binned mean and standard deviation. But yeah, this is sort of the end of my work. Um, a large time was spent on the data cleaning and obtaining the Alsacer variables. And then these last 2, 3 weeks have been on PSD values. But so outcomes wise for this research, we expect the PSD values to increase with proximity to the sun. Other papers demonstrate this. We kind of see this. We would like to see this more clearly with our data. So further effort should be expended towards verifying that. And then for all variables, the perpendicular component tends to be significantly greater than the parallel counterparts, as you could have seen in many of the past graphs. Personal outcomes for this project. I've gained a lot of experience using the Python data science stack, NumPys, Pandas, Matplotlib, Jupyter Labs. I'd never really used them before this internship, so this was a great exposure, and I'm very thankful for the experience. I've gotten a lot faster at making nice graphs. I also really enjoyed working in a research environment, and even though I'm very unfamiliar with this field, it was really neat to be able to contribute my CS knowledge and hear all of these really cool things be discovered. So as I've mentioned, for future improvement, we'd like to investigate the oddities and the PSD plots for Z minus, and identify why there's downward spikes in the colored PSD plots. I wanted to acknowledge the RIPP program and the for this opportunity and NSFF score for funding it. I want to give a massive thank you to Dr. Adhikari for all of his help, guidance, instruction, for answering all of my emails. They're not here with us today, but I want to thank the Bauer brothers for their assistance with the PSD stage. They're PhD students, and they helped me out a lot on the PSD stage. And then Jacob Post and Jason Jenkins, my colleagues, for having a nice workplace environment. Citations for the pictures I used, and then the papers I used throughout this project. Cool.
I'm Logan. My mentor was Dr. Nakano Otani, and this was our project. It was classifying particle motion in plasma using machine learning. Yeah, so as the industry moves forward and as things get much larger and more grand, so too does our data, right? So we're dealing with files of particles, millions of particles for hundreds of thousands to millions of time steps, in the sizes of many, many gigabytes to terabytes. And to put it lightly, that is very inefficient to go through just by humans, just by hands. So uh, people have been looking into using machine learning to help parse this data and do a lot of the heavy work for us to make it easier on us. And that's exactly what we were looking to as well, is how we could use that. A basic overview of our project here was we started off with basic simulation and physics, trying to implement that to get that working. And then we used a variety of different cases of different motions in plasma, as well as applying machine learning algorithms and such to it. So here are all the programs and the libraries that we have used in all of our programs, and you will see at the end that the entire code is been uploaded to GitHub, and you can go view it all for yourself. So just to start off, let me just go over some simulation terminology and what the simulations are. So particle in cell simulations are these large, complicated, widespread simulations that simulate particle motions on calculated, interpolated field meshes that have been fed in by the user. They're meant to be configurable and widely applicable from biological cells to plasma particles. And test particle simulations are more condensed, much simpler particle and cell simulations. They're more refined and more focused on a single task, but don't do as much. We found that it was far simpler to make our own test particle simulations than actually trying to learn a pre-existing particle in cell simulation. So as you see here, I guess test particle you could think of as a subset of a particle in cell simulator. Um, Here's all of the simulation physics and the equations needed for it, such as the equation for motion, as well as two different methods for simulation. There's a lot of numbers here, and there's a lot of variables, to which I don't need to really go into too much. I'm just going to say the Euler method simulates and moves every single time step. It is very simple to understand. It is just one formula, but it loses accuracy very quickly, and its accuracy is tied to how small the time step is. The Boris method updates every half time step, where it'll update the position and then the velocity. It's also called the leapfrog method for that reason. It's the default way of simulation for various particle simulators, and it's more accurate, but it's more expensive and less intuitive. So we implemented both just so we could see what the difference would be. And here's the difference. Given a uniform magnetic field with the properties there, what we're looking for is a perfect circle. And Bunin-Boris gives us that perfect circle, as you see from range 0 to -2 on Y and from -1 to 1 on the X axis. But let's see what this looks like in the Euler. Yeah, not quite the perfect circle we're looking for. As you can see on the y-axis, it goes from 150 to -150, and same for the x. So Euler seems to spiral out, while Bunin-Boris gives us the results we actually are looking for, and that's why we went forward with the Boris scheme for the rest of the project. So, so before I go over any of the actual like cases of the machine learning, it's probably best that we talk about what the process is that we're going to be applying to all of the simulation cases in the project. So the first thing we use is FFT transformation. It's a fast algorithm to apply Fourier transformation to all of the data of the particles that we are using to turn it from position over time to position frequency. This lets our clustering algorithms cluster based on patterns of motion rather than exactly where that pattern is happening at, allowing for more interesting and accurate clustering here. We do need to normalize this though, because the frequency does come back as complex numbers and none of it supports imaginary numbers. So the second thing we do here, which is the first real machine learning algorithm, is principal component analysis, which reduces our data set size while still keeping the percent of variation in our data to make it far faster for clustering. Um, as we see here with this second graph, you can see the number of principal components increasing over time, and you can see how much of the variance it keeps up. In our case, we wanted to keep at minimum 98.5% variance. And in one of our cases, it's turned one of our data sets from 10,000 by 600 into 10,000 by 5. While still keeping that variance. It's pretty powerful, pretty wild. So our main uh machine learning algorithm here, our main focus is k-means clustering, which is an unsupervised machine learning algorithm to partition a data set into a predetermined number of clusters. Uh, Unsupervised meaning that we let the computer do it all. We don't watch over it. We don't push it in the right direction. We don't label anything because it is very likely that data in the field is not labeled. So the computer is doing its own work to find these patterns. And that's what all the pre-processing, the normalization beforehand was there for, to increase the results of this and increase the accuracy of this. Our last bit here is a bit of a feature of k-means called silhouette analysis. When clustering, every sample is given a score between -1 and 1. The closer that score is to 1, the more fitting it is to clustering. The closer to 0, the less fit it is in the cluster. And with a negative value, it means that it's probably within the wrong cluster. It's best used for trimming out values that are not fit for clusters and are showing the best values. We go back to this picture right here where all the X's are the centers of the clusters. All the dots around the centers are the dots that have the highest scores, the closest to 1. All of the dots pretty far away from it, but still within the cluster, have a much lower score. And all the dots on the edges of the clusters here have the lowest score. That's also where the negative scores are likely to come in. And all this for plasma? Well, no, actually, this workflow is widely applicable. Here is an article right here applying it to 2D images of clothing and handbag here, doing the exact same things that we did, exact same process. They have gotten a computer to by itself determine between these handbags with straps and these handbags without straps, along with very other things of clothes. A couple shirts slip through, but I mean, we're not watching over it. If we're not watching over it, that's pretty good. So, with that out of the way, I want to move on to our first case, which is the magnetic cusp X-type case. Our objective here was to just get motion in a variable field for our simulation, as well as animate it in cluster segments. So what it is we are tracking particle motion in an X-type magnetic cusp field. These are the properties of that. This is a phase of the reconnection process, which is our final simulation. And here are some of our results with a little bit of a video outlining it. I can't really show all of it for time's sake, but this is we expanded the motion out long for it, and this is a far shorter thing of it. Main takeaway is there's chaotic middle motion before it shoots out onto one of the four axes. Um, and that's exactly what we wanted to do. We wanted to cluster the graph into segments of the chaotic middle motion, into transitionary motion between the center and the outer axes, as well as outer axes oscillations. This photo on the left here is us doing it with just 3 clusters to see what would happen if we did it like that. The photo on the right is we expanded out to 9 clusters. So we have redundant amount of clusters for the types we were looking for. And this gave us results that are far more interesting. As we can see, clusters 1, 3, and 6 both have middle motion, but clusters 1 and 3 seem to be more middle motion, like bouncing between axes, while cluster 6 seems to be solely chaotic motion. So, our takeaway here was that dynamic fields are complicated, and that the higher number of clusters with redundant numbers of clusters, we get more interesting results that we probably would not have seen because all of the transitionary motion of 1 and 3 got just grouped into one of the clusters and when we lowered the amount. So for case 2, I'm gonna just breeze through this one because this is not as relevant to our research, but it was really good practice for just figuring out how to cluster not segments but full on graphs here because we used scaled Brownian motion to create anomalous diffusion charts, which is essentially an algorithm where we feed it one parameter and it spits back out at us a random graph depending on the number based on we were looking at 3 categories, which are subdiffusion, normal diffusion, and super diffusion. The main like difference between all these categories is their ranges, which if you look at the Y values, subdiffusion's very small, normal's a little larger, super diffusion's far larger. So what we did was we made 1,000 of each, just combined them together and threw it at the machine to see what it would do. We first started with position based, and it found some interesting patterns in the position. It also found patterns that were mirrored. So as you see with like clusters 2 and 4 and 1, a lot of what's going on with the movement going up is also what's going on down is kind of like reflected. But we wanted to see if it could by position cluster it based on the 3 types correctly, and it could not. It ended up putting 72% of clusters into what it saw as subdiffusion and left out the rest of it. So then we passed in not the positional values, but the velocity values to the program, and then it was able to get this out correctly to us. So our takeaways here were clustering based on positions, an interesting way to group motions of patterns and find motions of patterns, but it's not accurate when you're trying to find like results that you know you're wanting to find, where velocity is far more accurate. Also, I'm sorry, my webcam's not the best if you see glitching like that. But that's our takeaway here. And then this magnetic reconnection is our last and largest case. We have several objectives: mass particle simulation, simulation of 2 particle types, electrons and ions, as well as interpolating field data, and whatnot. So what is magnetic reconnection? It's a common phenomenon occurring in space, astrophysical and fusion plasmas, where 2 distinct topologies connect and reconfigure, turning some of that magnetic field energy into kinetic field energy. Um, it's also responsible for a lot of the behavior in our magnetosphere, such as auroras, as well as some disturbances in higher technical plasma technology. It's like something we need to work around. Here's the flow chart for the program because before this case, every single case was kind of done in a single file, but we thought, and I knew it like for certain it would get too bloated if we tried to do it in one file. So we split it up here. We read in data files for the different fields. We interpolated the fields into a simulation. Then we outputted the simulations to go to a machine learning file. Now, for fields and magnetic reconnection has its electric and magnetic fields change and evolve over time, as you see here. Since we can't really feasibly do that while staying anywhere efficient, we took just a single snippet out of this of a single portion, later portion of magnetic reconnection, then having it vary over time as well. That being what you see here, this is the exact snippet that we've taken out of magnetic reconnection for our case here. Now, for interpolating field data, since all the data was just grids of 200 by 512, we took where the plasma particles position is X and Y, and we rounded the values down, and then we took that data out um, and compare it to where it was in the graph to take the data out from there, because not doing so would not let us do that using our optimization. So it would go from taking 30 seconds to simulate 10,000 particles to taking many hours, as well as we just couldn't figure out how to do it. So we just used nearest neighbor and rounded the values here. So here's the simulation details. All of our ions have a mass of one, a charge of one. We are using 10,000 of them with a time step of zero point 0.1 and 10,000 time steps. Our electrons have a 1/100th of that mass, a negative one charge. We're using a 100 times less, as well as we're using a 100 times smaller time scale and number of time steps. Um, and we're slicing it down to be 200 through or 2,000 through 5,000 and 200,000 through 500,000, since we found this is where a majority of the motion we're looking for is. As you can see here, this is what the ion graph looked like before we took out everything, and then this is what it looks like afterward. So it preserves a lot of that interesting motion. It doesn't really do too much of the same. It kind of looks like it gets rid of a lot of interesting motion here, but if you zoom in the electron sliced, it's still pretty interesting what we're looking at here. All right, so for clustering, we wanted to see what would happen if we clustered based on position, velocity, and a hybrid of both. For our ions, I use silhouette analysis to display the 50 best fit samples per cluster, but since there's not that many electrons, we just did every single electron per cluster. So here is clustering based on position for the ions. Here is it for the based on velocity. And then here it is based on both. It's pretty much the same. There's some percentage differences, like if you look at cluster 10, but for the most part, same thing. And here is the electrons. Here's it clustering based on position, based on velocity, and I'm pretty sure between velocity and position, electrons do not change at all. Um, so here it is, and project takeaways here. In the age of exponentially growing data sets, machine learning gives us a tangible way of dissecting and understanding these sets, as well as finding patterns and groupings we would have never thought of otherwise. You can check out the code here, as well as a Google Drive link to all of the figures and the data files used in it. And here is just the image credits for everything used, as well as additional readings and sources for what we used in our research.
Hello, my name is Thomas Farrell. I am a junior from University of Arkansas visiting UAH as an intern this summer. I'm working under Dr. Lin Zhao. She has been my mentor for the past 8 or so weeks. The name of my project is the relationship between velocity and density fluctuations in the outer heliosphere. Um, it has been an eye-opening process. I'm glad I've been able to be on this project. Dr. Uh, Zhao has been a wonderful mentor. Um, so the outline slash general purpose of this uh, project has been to analyze and look for sort of disruptions in the velocity, density, and magnetic variables as they radially increase as distance from the sun. Um, and the way we wanted to do that was to perform different types of spectral analysis on the data to see what sort of trends, see how any of those trends correlates, and basically also to see how any of those trends are disrupted because of interstellar pickup ions. Um, and so the sort of analysis that we wanted to perform was partial spectral density and a wavelet analysis to produce some sort of scalo or spectrogram. And so we decided to use Voyager 2 measurements, which the plasma wave during that during that time, the measurements were averaged out, I think like 18 seconds, and then every four was averaged, and so it's 96 seconds, and then mag 48 seconds. Let's see. So a little background. So our solar environment, like the way that the Earth is moving through space, the sun is also moving through space, and it carries its own environment through density, like of just gas, dust, carries us along with it. And the point at where it reaches, or sort of ejections from the sun, which that's what we're focusing on, solar wind, reach the end of the heliosphere. It's called the heliopause, and that's when sort of the expanding process of solar wind comes against the background, or the forces equal to the background particles and ions, which are typically the most populating ion in interstellar space is hydrogen ions. So that's the one that's most checked for. So we wanted to see how, when plasma waves encounter interstellar ions, they ionize them as well. And we wanted to see what kind of disruptions this ionization and slash accumulation does to the general trends. It disrupts heating, creates disruptions in the non-adiabatic heating process. And so we were hoping to see that some of those disruptions were visible in some of the analysis that we did. A quick look at the data that we're using. Again, it's Voyager. We're using it from the first half of 1979. 4 to 6 AU is about its radial distance from the sun. This is just goes up to the point about before the intersection with the path of Jupiter. So top left is a graph just about like latitude, longitude, and radial developments throughout this period. You can see it's pretty steady. And then beneath that is New Horizon and Voyager 2 at that time. And then the top right is velocity in the RTN coordinate system measurements. And you can see that there's a lot of gaps. And the graph below is also focused on that. The y-axis is the frequency of that gap in data appears in the portion of data that we picked out. And we picked out this data because generally there's, for some of the reconstruction we do later, it's about 30% of this data is missing. And for some of the reconstruction methods we're going to be using later, 30% it's like the point where it becomes mostly disruptive to like the original structure of the data when they try to reconstruct with anything more than that. So first we performed power spectral density function on it to see how it increases radial distance. And we found that it decreased with increasing frequency, which is pretty consistent with the nature of cascading turbulence as it expands. During this time, I was working a lot with CDA Web using the interface online, but I found some better tools like CDA SWS is good. one, so you can just use it right in the Python notebook without having to go onto the actual website. But for some of the other processes later on, I moved on to MATLAB, which I was previously unfamiliar with, but I was fortunate to have a subscription to the service. So next we wanted to see to perform a wavelet analysis, or to get like a scalegram from this data to see frequency and time dependence. And but we wanted to do a continuous wavelet analysis, but the data had gaps, as previously mentioned. So we wanted to perform compressed sensing. And so this I wrote up in MATLAB, used the SPGL1, which was what I think what Logan was talking about, the Fourier transform. Yeah, it's the Fourier transform we used for this. And then once I did that in MATLAB, I reconstructed the velocities. And this is basically the trends. I'm sorry I messed up the radial tangential normal. I got them the wrong order there. But and I also redid the power spectral density function on the mag values and saw that it fit with like the negative 5/3 slope, which is the Kolmogorov turbulence, which is basically just like the consistent rate of cascading turbulence as it expands. And so I also performed the wavelet analysis while I was in MATLAB. So there's a high range of I got a great email. A high range of frequencies over, or a high range of power over higher frequencies per velocity, and more variation across a lot of different other V velocities. And there's a lot of streaks out in the B magnitude values, which I think could be indicative of some wave or interrupting structures. And down at the bottom are wavelet correlations between density and V, which was in an effort to see if there's any sort of disruptions in the two correlations we are investigating. And I don't really know what I could make out from this, but I think it was important that I had compiled this all together, because I've got it down to a fairly standard process of data acquisition, cleaning, and reconstruction and analysis. So I'm happy that I've done this and can pass it on to the next person who comes on after me. I'd like to thank everyone involved in this program. I'd like to thank my mentor. I'd like to thank the people involved with making this happen. Thank you very much.
Good afternoon, everyone. My name is Jason Jenkins, and this is the research that I did over the summer with the FTPP, Future Technologies Enabling Plasma Processes. I worked with Dr. Laxman Adhikari with the PUI-driven turbulence along the trajectory of New Horizons. And so what we worked with is the pickup ions and solar winds. So pickup ions are created when interstellar neutral atoms resonantly exchange charge with the solar wind. The New Horizons solar wind around Pluto, which is the SWAP instrument, has provided observations of interstellar hydrogen pickup ions in the outer heliosphere. One of the noticeable effects of these pickup ions is a gradual decrease in the solar wind speed with increase in distance. And to the right of your screen, we have the solar wind and the New Horizons spacecraft with the SWAP instrument being pointed out. Here we have the data from two different spacecraft that we used throughout my internship, with Omni being on the left and New Horizons being on the right. Uh, the data we utilized was its distance, speed, density, temperature, and its spatial coordinates of latitude and longitude in with respect to time. All of it is with respect to time. All right, this basically shows the part of of space where the termination shot of where the interstellar medium where the neutral atoms are coming from and actually meet the solar wind. This is where the pickup ions are created, so to speak. So energy and velocity distribution is very keen with our research. The pickup ions often exhibit different energy and velocity distributions compared to the background solar wind ions. To find the density and pressure of pickup ions behind the termination shock, one can show that the decrease in the kinetic energy of the mixture at the termination shock predominantly contributed to the increase in the pressure of pickup ions. And as you can see from the data that I was able to create these graphs over here of the speed at which Omni at the bottom took a reading of the solar wind, and at the top is New Horizons. And so what I did was I took the speed that the solar wind was going when it was read by Omni, and calculated the time out to where New Horizons was to take another reading of the speed of the solar wind. And as you can tell, the solar wind is actually decreasing. And these hydrogen pickup ions usually are found in a range of charge from 0.1 kilo electron volt to 1 kilo electron volt. And we'll see here on the next slide. So the speed and density and turbulence distribution as the New Horizons SWAP instrument records solar wind conditions as the spacecraft travels through the outer heliosphere. The data reveals a gradual decrease in solar wind speed with the increasing distance from the sun. Additionally, the data shows. Hold on a second. This box pulled. Hold on a second. I'm trying to get this box off my screen. It picked up the speaker beside me. I'm sorry. Okay. Now can you hear me fine? Can everyone hear me?
Yes.
Okay. All right. So, as I was saying, additionally, the data shows an increase in plasma density in regions where pickup ions are more prevalent. Turbulence in the solar wind is characterized by fluctuations in velocity and density. Pickup ions contribute to this turbulence by adding energy and momentum to the solar wind flow. The analysis of density and speed data along the trajectory of New Horizons suggests regions of enhanced turbulence, particularly where there is a noticeable increase in plasma density. And as you can see here at New Horizons, the top you can tell as the distance as New Horizons is the distance is accelerating or getting farther away. You see that the speed at which the solar wind is actually decreasing, and at the bottom, that same within the same reading as the spacecraft is traveling farther out into space, the density of these pickup ions actually increase as you can tell. So it's, in other words, these hydrogen neutrals are actually meeting the solar wind, causing it to slow down and the density to go up from where the charge exchange is. Implications for space missions. Hold on. Oh, never mind. There we go. So understanding the impact of pickup ions on solar wind turbulence is crucial for space missions. Turbulence can affect spacecraft communication and navigation systems. The insights gained from the New Horizons missions help in designing better protective measures and improving the reliability of future missions. This is the trajectory at which New Horizons is on right now. All right. And my conclusion, the analysis of data from the Omni and New Horizons probes highlights the significant role of pickup ions in driving plasma turbulence in the heliosphere. The observed variations in plasma density and solar wind speed provide evidence of these interactions along the trajectory of New Horizons. Further studies and continuous monitoring are essential to deepen our understanding of these phenomena and their implications for the space exploration. And this is my acknowledgement showing I used Dr. Adhikari's 2 papers that were very well written, and I definitely had to do my research at really understanding the complexity of the solar wind and the magnetohydrodynamic turbulence. So I just want to thank Dr. Adhikari for allowing me, this time to do this research with him, and for being able to read his work. He's definitely an amazing scientist.
Okay, hello everyone, and it's my pleasure to introduce our speaker today, Yahia Gadala, who has been working. He's a student at UAH, but this summer he's been working with us here at UAB in the Department of Physics, and he's been working with myself, Renato Camara, and also with our graduate students, Zar Nasiri and Dorian Carpenter. It's been a great team to work this summer. And Yahia's project is entitled Strontium Titanate Homoepitaxial Growth by Post-Laser Deposition, and it's in situ monitoring using reflection high-energy electron diffraction. Turn it over to you, Yahia. Thank you.
Thank you, Dr. Kamada. So yes, as he said, we've been working on the homoepitaxial growth of strontium titanate. I've provided 3 pictures here on the title screen of different diffraction patterns from the read and then the data we get. I'd also like to take a moment to acknowledge our funding, the National Science Foundation, and we are part of the Future Technologies and Enabling of Plasma Processes Consortium. But let's get started. So we start off the story with epitaxy. Epitaxy is the crystalline growth of a material with an orientation matching the crystal structure of the substrate it is being deposited onto. By changing experimental parameters, the quality of the thin film is affected. Now, for our purposes, the variable of focus was the substrate temperature. You might also change the laser repetition rate, fluence, and background pressure, all to adjust your level of control of thin film growth. Now, the process we used to deposit was pulsed laser deposition, and it is a common procedure associated with epitaxial growth. In PLD, a pulsating laser vaporizes and ionizes target atoms into an expanding plasma. These ions land on the substrate and then condense to form a thin film. The growth of this thin film follows a 2-step model, and it includes nucleation of the atoms and then growth of crystalline layers. Here, I have provided a schematic of our vacuum chamber. You can see our expanding cold plasma plume, our target on a rotating motor, our substrate on a heated dish covered by a plate with a small hole for the plasma to hit onto our desired substrate, because as you see, there are multiple. You'll also see an electron gun, an exaggerated electron gun. I'll show a more accurate figure later on. And then other parameters in the experiment, and you'll notice the words algorithmically controlled. And this is important because our eventual goal is to automate this process. Now, let's start the story off with reflection high energy electron diffraction, or READ for short. To grow quality thin films, real-time monitoring of the structures are needed, and it can be achieved through READ. Now, strontium titanate, or STO, is commonly used as a substrate in PLD. This is from its perovskite structure. In this experiment, we have grown thin STO layers onto STO substrates, a process referred to as homoepitaxy. we used a krypton fluoride excimer laser with a 248 nanometer wavelength and around 0.7 joule per centimeter squared fluence to ablate an STO target and deposit onto substrates at 540 degrees Celsius and 640 degrees Celsius in separate trials. Here is a figure of our read. As the basic idea of read is very simple in principle. I, in fact, took this figure from Wikipedia just to illustrate the skin and bones of a read experimental setup. For a read, we use an electron gun to shoot a focused beam of electrons at a very small incident angle that gets reflected onto a phosphor screen with a CCD camera out here recording the specular reflection intensity. Now, we use a small angle for one, a larger capture area on the substrate, and two, so the electrons do not penetrate too deeply into the crystal lattice. Now, we mentioned earlier a quality thin film, but what constitutes this? This is from 2D or 3D growth. Now, the ideal thin film is one in which all of its atoms are arranged in subsequent layers on top of one another, all in one orientation. This is called layer by layer thin film growth, and it follows the so-called Frank von der Merwe model. I will be referring it to as the FVDW. However, this is just one of several possible ways the film may grow. If growth of the thin film is following an FVDW model, oscillations are observed in the intensity of the read specular reflection. On the other hand, 3D island growth results in a rapidly decaying intensities due to the development of surface roughness. These images are of the diffraction pattern from the read. On the left, we see a streak. This is a sign of a successful monolayer being deposited. On the right, we see points, diffraction points, and this is just the read aimed at a niobidium-doped STO substrate at room temperature while we were aligning the read. But these different points all correspond. You can get so much information from these points, including atomic spacings, etc. But just to show how useful our read is. Here I have provided a figure to talk about the difference between diffuse scattering and specular reflection. On the left, we see 3 crystal lattice planes. These are the surfaces of a crystal lattice here. And then an incoming wavelength of light or electrons, and due to the wave-like particle duality of electrons, we can say either one. Now, the specular reflection, we see a wavelength hit the top surface and then create a 0th order specular reflection. Now, the terminology here is important. Some of the electrons will continue in the crystal lattice and create a first, second, and so forth onto the nth orders as deep as it can penetrate. Now, each of these reflections correspond to a diffraction point here. On the right, we see something called this diffuse scattering. This is from the surface interaction between reflecting rays and the growing crystals in the depositing thin films. What happens is as the thin film grows, it creates tiny surfaces with different angles so that the light may hit it and reflect at the same angle, the same and opposite. So this causes light to scatter in all different directions due to the randomness of the orientation of growing crystals. But let's get into the read observation data. Here I have provided rapid decay or 3D growth of STO. We see the deposition begins and ends very quickly, meaning that there's no oscillation. This was deposition done at 540 degrees Celsius with a laser repetition rate of 1 Hertz, energy of 57 millijoules, a spot area of around 8.208 millimeters squared, and a pressure of 3.8 times 10 to the minus 6 torr. And this tiny figure here is a polynomial fitting of the deposition data from 60 to 120 seconds. And this is important for our machine learning algorithms and being able to use our Bayesian optimization, which is what we hope to automate this process. Now we have 2D growth. We see what I want you to focus on here are these bigger oscillations that I'm tracing out with the laser pointer. Now there is going to be a lot of noise because different things may interfere with our capturing of the data, such as the substrate motor, um, intrinsic defects in the molecular structure, and etc. There are so many different reasons that a new frequency may be introduced. But if you are able to do a polynomial fitting, we can kind of clean the data and get um, a more accurate representation of the growing thin film and its atomic flatness. So here we have deposition done at 650 degrees Celsius with the same, with the rest of the parameters being the same, except for the energy here. Note it went from 57 to 54.9. Now, one important detail is here the intensity variation was modeled with a two frequency oscillation, one at 0.04 hertz and one at 0.02, or approximate. This is likely due to the inhomogeneity of the atomic flux over sample area. What this means is as the target is rotating and the PLD is hitting it, it's not hitting with the same energy every time. Well, it's the same energy, but there might not be the same amount of STO and all over. It might not be so uniform on the target. So the deposition rate won't be uniform either. Okay, this introduces a new frequency and why we have chosen to do a two frequency fit. Now, both of the situations I've shown to you so far were isolated. Now, we are trying to create a buffer layer, so we're doing more isolated events. But for the most part, our data will look like this. This is, as you can see, a lot more complicated, but indicates much more successful deposition. We see here from the very high increase in intensity that the atomic flatness was better than the polished STO substrate it started with. Now, this area of noise is consistent with two frequency oscillations, meaning that we have a basis to stand on with our two frequency fit. Now, this deposition was also done at 650 degrees Celsius with a repetition rate of 1 hertz, an energy of 54.9 millijoules, a spot area of 8.208 millimeters squared, and a pressure of around 3.8 times 10 to the minus 6 torr. One important thing to note is the benefits of pausing deposition. When we pause the deposition, we allow the heat that we are placing onto the substrate to shake the atoms. Imagine having a bucket of sand poured into a pan. You'll first start with an island of sand, but the heat when you shake the pan and you let it flatten out like this is a metaphor to what the heat is doing to our thin film. It wobbles the atoms until they find a place to lodge themselves. And I'll show you another example here where we pause for 10 seconds and a spike in intensity is observed. Now, although I am very blessed to have the opportunity to learn under the guidance of Dr. Renato Kamada and his team, I am also responsible for contributing to this project. So here are my highlights for considerable contributions. I and Dorian Carpenter set up the turbo pump and connected the TCU controller to it so we may have easy access on the control panel. I also designed the metal sleeve to be manufactured by Mr. Jerry Sewell of the UAB machine shop. The purpose of this part is to hold a lead-embedded glass piece so that it will allow us to see into the experiment and protect us from X-rays emitted from decelerating electrons, leaving the thin film surface from read. Lastly, I acquired and assisted in acquisition of read data during PLD under various conditions. In conclusion, we set up and tested a read system for monitoring the thin film growth during pulse laser deposition. We upgraded the vacuum system by installing a turbo pump and TCU controller to allow for pressures of 10 to the minus 7 torr and easy access to supplying or stopping power to the pumps. We acquired read data of deposition of STO onto STO or homoepitaxy at different temperatures. At 540 degrees Celsius, we see three-dimensional growth, and at 650 degrees Celsius, growth is layer by layer, so read oscillations are observed. The acquired read data will be useful as input to our machine learning algorithm under development by Mr. Zahar Nassiri for automation of the PLD process. I'd like to take a moment to acknowledge the National Science Foundation again, and we are very grateful to Mr. Jerval Leggett for assistance in setting up our read system and to Mr. Nitesh Peligri for his contributions in designing our apparatus. Now, just to take a moment to look at the team and thank you very much for listening to me today.
Hi guys, I'm Joshua Perry. I'm doing a FTPP internship here at Auburn. I was mentored by SciCat. This summer I worked on the development of multi-purpose dusty plasma devices for studying UV photonization dust and dust transport. What are plasmas? Well, plasma is the fourth state of matter. The other three states you have solid, liquid, and gas. You know, to go from solid to liquid, you melt. From liquid to gas, you heat it up. And so to go from gas to plasma, you need even hotter because plasma is over 1,000 times hotter than gas, regular gas. So we need an ionized gas to be able to make plasma. Reasons for creating a laboratory plasma device. Plasma is very common in the universe with lightning, the northern lights, but plasma occurring like on Earth, actually on Earth, just not in our atmosphere, is pretty rare because Earth is cold relative to plasmas. And plasmas usually need to be very hot. As I said, they're 1,000 times hotter than gas. And laboratory plasma devices give us a controlled environment for the plasma to be able to safely produce and study. And there are various kinds of laboratory plasma devices depending on the context and what type of studies are being done and conducted. And these are some examples of some large-scale plasma devices here at Auburn. On the left, we have MDPX, or magnetized dusty plasma experiment. And in this is basically a big magnet. I think it gets to the 10 to the 5 or 6 Tesla. And dusty plasmas are exposed to a magnetic field in there. And so then on the right, we have Auburn linear experiment on instability studies, nicknamed Alexis. And it's a study for it's like an inductively coiled RF source for the plasma, and plasma turbulence is kind of a main point in this. And a recipe for building a tabletop plasma device, we need to build a chamber that can achieve a low pressure as necessary. Need to make sure there are no vacuum leaks, ensure that the working gas is flowing at our required rate, and build an electrical system to deliver high voltage to the plasma. We can use a RF source, which we use here at Auburn at 13.56 megahertz, or a high voltage DC power. Creating a low pressure chamber, we have to close all openings to the outside atmosphere, use a pressure gauge to make sure our pressure is known at all times, use a roughing pump, which helps us get down to the 5 to 10 millitore range. You can use a turbo pump too, but for a tabletop plasma device, we don't need to get down really past the 5 to 10 millitore range to really make a good plasma. And knowing how to perform leak checking is actually important when creating this chamber as well. You can probe around the different connections with isopropanol, because it might actually be like a broken O-ring or something, or a weak connection, something isn't tight. And here's a picture of an O-ring. They come in different sizes. I think this is like the 16 centimeter or something in diameter O-ring. But yeah, we put those inside the connections because they expand and help us keep a tight vacuum. And these are some pictures on the different steps when creating a low pressure chamber. On the left here, we have the roughing pump that takes air out, creates helps us get down to the pressures we need, and then the pressure gauge that checks the pressure at all times, reading the pressure. And then this is the 2 6-way cross after it was finished. You can see we got multimeters hooked up to it, lasers, some optical windows for some viewing, and yeah. And ensuring controlled gas flow, you need a pressurized ultra pure gas, helium, argon, neon, krypton. Here we use argon, and when you make a plasma with argon, it actually makes a pink glow, which we'll see later. And you need to use a mass flow controller to adjust the gas flow rates into the chamber, and the pressure of the chamber needs to be checked. And you also need a vent valve for air to escape, because You might have a vacuum leak, or you might need to make some changes to your chamber, add in some windows, or putting the electrode in a different way. So you need that vent valve, so you don't have to wait for it to break vacuum very long, because it's going to take a while. And on the left, this is the mass flow controller. We set it to like 3 or 4 SCCM to get a good plasma. And then on the right, you have a bottle of argon connected to the mass flow controller, just how it's like set up. And you need Teflon tape on those connections too to really make it tight, so that gas isn't just escaping. And powering electrodes to ionize gas, you need to design an electrode. We use electrodes here at Auburn in the shapes of like a disc. It creates a capacity coupled plasmas and ensure proper electrical connectivity. That's why you saw the multimeters on it. Make sure we're grounded correctly. And use either RF or DC power supply. You can use the DC power supplies to like bias the plasma in a certain way. And ensure safe operation. We check the proper grounding with our multimeter, and we check gas flow, and you turn on the power, and you have a plasma. And so this is just more talking about powering the electrodes, and you have to be aware of your BNC connections when you're making that electrode. Make sure you have the right connections to actually connect it to your matching network. So some examples of dusty plasmas built at Auburn during the REU program was the two-way 6-cross, as you saw earlier, that I worked on. It was used to study the effect of UV photonization. And then the modular cube, which we'll see later, to study lunar dust transport. And the modular octagon that was used to study dust crystal formation. In each chamber, we use 2 electrodes, both of which can be either connected to RF or DC power supplies. And in each chamber, we use a mechanism to introduce dust. You can either use a shaker, or you can put the DCA electrode on like the bottom and arc it into the plasma, arc the dust into the plasma. And so these are some pictures of the vacuum chamber. This is just it fully set up on the left, and on the right we have what it looks like with the plasma through the optical window. I think we only had it running at 1 SCCM right here, so the plasma isn't like that strong here, but it's still there. And this is the modular cube. As you can see, that bottom disc, that's our DC electrode, and the green light is the laser, so you can see the dust when it's in the plasma. And then this is the octagonal chamber. I thought this was really cool. Really get to see that pink glow from the argon of the plasma being made here. It's really pretty. And thank you for listening to my talk.